Hey everyone, I'm going to start today with an advert. So let me just share my screen. This year, actually, we're going to have a new program at HKUST where we admit people for Master of Philosophy and PhD degrees in financial technology. And you can see the link here. Please apply to this if you're interested in the kind of material that you're seeing in this course, and if you want to do this as a master's student or as a PhD student. I will actually myself take a few students from this program this year, so if you like to work with me as a master's student, you can also apply here. This will be based in our Guangzhou campus. And actually the deadline for applying for the financial technology or fintech MPhil and PhD programs is 1st of March. So if you are interested in this, you should apply as soon as possible. Okay, so this was the small ad that I wanted to give you. And now let's go back to the course. So if you remember the very first session, I talked a bit about what we want to do when we want to have a cryptocurrency. And I talked about the properties that our ideal currency would have. And I talked about decentralization, why we need it, and the privacy properties that we want to have. For example, we want to make sure that no one's identity is known to others. We want to make sure that transactions are private. We talked about this idea of being trustless, that we don't want to really trust anyone, but make sure that everything goes through using cryptography. And we also talked about the most important thing, which was decentralization. We said we don't want to have a central bank. We don't want to have any kind of central authority that can control the system. And ideally, what we want is that we want all users to be 100% equal. Then in the past few sessions, we went over all the cryptography that we need in order to achieve this. So I talked to you about symmetric cryptography, RSA, which is, I talked about symmetric cryptography such as one-time pad, and I also talked to you about public key crypto such as RSA. In the last session, we talked about digital signatures, and this idea that we can use digital signatures to prove that a specific message comes from a specific person. And we also, of course, talked about cryptographic hash functions. We talked about this idea that hash functions can be used as digests, that they can be used to commit to something, and that they can be used for creating data structures such as a Merkle tree. Now we are finally going to get out of the classical cryptography world and go into cryptocurrencies. So this session is going to be all focused on us creating our own cryptocurrency. And at the end of this session, we will get to proof of work, but I will mostly leave proof of work and proof of stake for next sessions. So let me just go over here. There was one question at the end of the previous session when everyone had almost left that I think is worth going over again. So last session, at the end of the session, someone asked about combining these digital signatures with the RSA cryptography, the public key cryptography that we had here. So in the first scenario, when we were doing public key cryptography, the idea was that Alice wants to send a message to Bob, and the only thing that we want to make sure is that only Bob can read that message, right? And the idea here was that Alice can encrypt the message using Bob's public key, and then send the message to Bob, and then only Bob can decrypt it. Then we had this other scenario with digital signatures, and the idea here was that Bob sends a message to Alice, and we don't want this message to be private. This message is public, but we want to be able to prove to Alice that this message actually came from Bob. So now, again, we said that Bob will have a secret key or a private key and a public key. And we talked about how we can make a signature like this. But in practice, in a lot of scenarios, what happens is that we want the message to be both private and authenticated. So we want to make sure that the message comes from whoever claims that the message is coming from them. And we also want to make sure that no one else can read the message other than the intended recipient. Okay? And in these cases, we have to actually mix the two ideas that we have here. We have to mix the idea of basic RSA and RSA digital signatures, let's say. So if Bob wants to send a message to Alice and wants to make sure that this message can only be read by Alice and that Alice is convinced that it's coming from Bob, what Bob does is that he first takes his message and signs it using his own secret key. Then he encrypts the whole message, so the original message and the signature, using Alice's public key, and sends that encrypted message to Alice. So now only Alice can decrypt the message, and when she decrypts it, she sees the main message and also a signature. And she can then verify the signature and make sure that the message came from Bob. So this is how we would usually mix these two ideas and use them together. Okay. Yeah, but enough of that. Let's actually go to the main topic of this session, which is how we can make a cryptocurrency. So if we want to have a cryptocurrency, one of the first problems that we have to solve is the problem of figuring out identities. By definition, in a currency system, you will have different people or different entities, and these people or entities are going to send and receive money using this currency. So we need a way of identifying them, because if I want to send some money to you, I have to have a way of actually referring to you and saying that this is the place or the person who is going to get my money. And one of the really prominent ideas here, and something that is actually quite easy to come up with, is to use public keys as identities. So if we go back here, remember that each person can have a private key and a public key. And actually they can have as many of these as they want, because we talked about key generation, I think, in the last session. And we showed that anyone can generate keys for themselves. So we can just say that we refer to anyone on the network using their public key. This has several benefits. So the first benefit is that you can create as many public keys as you like. And these keys are not really connected immediately to your real-world identity. That means you have some level of privacy, because you can have as many public keys as you like and you don't have to connect them to your identity. But it also means that others can refer to you, at least they can refer to some of your public keys, and they can send you money. So let me just write it here. The identity of a person is just the same as their public key. And there is no uniqueness. So again, as I said, anyone can create as many public key and secret keys as they like. And this also has a bunch of other good properties. So we can authenticate the messages, for example. Suppose that I have 10 coins, and I know that these 10 coins belong to someone with this particular public key. Then whenever they want to spend it, I expect a signature on it, and that signature should correspond to the public key. So it should have been created using the secret key that matches that public key. right? So with these kinds of identities, we can also have signatures on messages. So that means we can authenticate any message that is on the network. And also, as I said, we have some level of privacy. We don't really have anonymity if we use these kinds of identities, but we have what we call pseudonymity. I'm not sure how to use that, but anyway. So what that means is that when you see actions on the network, when you see that someone is sending money to someone else, what you will see is the identities of these people as their public key. So you don't know their real world identity, but you know the public key that is sending, for example, 5 Bitcoins to this other public key. And what that means is that if you do a lot of transactions with the same identity, with the same public key, then people would be able to actually piece this together and say, these transactions probably come from the same person. So you don't have perfect privacy and perfect anonymity, but at the same time, it's not so easy to connect your real world identity to it. Okay? And just one more point that I would say about using public key as identity is that in Bitcoin, actually, we use the hash of the public key as an identity. And the reason for taking the hash is that public keys are usually long, so we just prefer to have a shorter digest of them. I'll just write it here. It's not really technically important, since at the end of the day, we're going to do all of our verifications and authentications using the public key itself. But in Bitcoin, we use the hash of the public key as identity. This is the first design choice that we make. And already, if you look at this, it has that kind of decentralization in mind, the idea that everyone is equal. So we don't have a centralized place that will give out accounts. You don't have to go and sign up with a particular bank or a particular company or anything like that. Signing up is basically just creating your secret key and public key pair, which, as we saw in the previous sessions, anyone can do, and anyone can create as many identities as they like. So already we know that signing up is a decentralized thing in this system. Okay, so there is a question that says, do you mean if two public keys always have transactions, they probably have some relationship regarding the pseudonymity? Okay, so let me just answer this question first. So what you will see on the blockchain, and later on I will talk about the blockchain itself, is a bunch of transactions that says that this person, which means this public key, sent this much money to that public key. Now, suppose that you have a public key for yourself. So let's say you've created an account or an identity for yourself, and you have a bunch of Bitcoins there. And then suppose that you send some of this Bitcoin to your friend, or maybe you use some of this Bitcoin to avoid paying taxes or something. And then you use the same public key and the Bitcoins that were stored for the same public key to buy a coffee, for example, at Starbucks. Then what might happen is that maybe at Starbucks they have a camera and they can see your face. So maybe there is a chance that they can connect this public key that you use to pay for your coffee to your real world identity. But if that happens, then not only that transaction is connected to your real world identity, but also all the transactions that you have made using that same public key. So in that sense, the transactions are not really anonymous. because they're always connected to a public key. And if you make a mistake and you somehow connect your public key to your real world identity, then all of them will be connected to your real world identity. But there are many defenses against this. One simple thing you can do, for example, is to have many public keys. There's nothing that stops you from creating as many public key and secret keys as you like. So just create as many identities as you need. Okay. So there is another question that says, so if person A is sending person B money, person A uses person B's public key to encrypt, but then how does person B know who it is being sent from? No, actually sending money is going to be much more complicated than this. So sending money is not the same as just sending a message to someone. I will cover it, and it's going to take a lot of time. So for now, my only answer to that question is no, that's not how we send money. Okay. So for now, we know how to manage identities in our network or in our currency system. But the next question is, how do we keep track of who owns what? And there are two classical ways that we can keep track of, let's say, ownership. And the first way of doing this is that we can have an account for each person, and this account can have a balance. So we know how much money this particular person has. Actually, it turns out this is not such a great idea for having a cryptocurrency. And Bitcoin goes with a different design. And personally, I think this is a better design. And the design in Bitcoin is that transactions are the first class objects. So the most important unit is a transaction. And the way it works is that each transaction, so suppose this is a transaction, and I just write TX for transaction all the time. Okay. So each transaction has a bunch of inputs and a bunch of outputs. And you can think of inputs as money flowing into this transaction and outputs as money flowing out of this transaction. So each output would be, for example, in the simplest case, just would contain the public key of the new owner. And each input is the output of a previous transaction. Okay? So for example, let me give you an example to clear this up. Let's say Alice wants to send 5 Bitcoins to Bob. And I know that with the current exchange rate, this is so much money, but let's just say this is what's going to happen. Well, first of all, Alice should own 5 Bitcoins, right? So there should be some previous transaction in which Alice received Bitcoins. So there is, suppose, some transaction, let's call it transaction 1, in which there was an output that said, we have 5 Bitcoins, 5 Bitcoins belonging to Alice. So someone else had sent 5 Bitcoins to Alice's public key. So I say belonging to Alice, but again, remember, all of our identities are public keys. So what we actually do is that we say it belongs to anyone who has a public key that has this particular hash. But instead of doing that, I just say belonging to Alice. So first, she has to find such a transaction that has such an output, and then she can form a new transaction. Let's call this transaction, for example, transaction 2. And what Alice does is that she uses this output that paid her money as an input to this transaction. Okay? And she creates an output for this transaction which says 5 Bitcoins are now belonging to Bob. So just gives and creates an output in which the amount of the output is 5 Bitcoins and the new owner is Bob. So this is how we would create a transaction. And so the way you can think about this is that each transaction should tell where the money is coming from, and the money can only come from previous transactions. So if you're spending some money, you should have earned that money in some previous transaction. And then it also says where the money goes to. So in this case, we say this 5 Bitcoins go to Bob. And those are the meanings of input and output in our transactions. Okay? So I will come back and actually answer your questions a little bit later because I have to cover a little bit more about these transactions. So there are several questions. First of all, how do we authenticate these transactions? Well, the authentication in this case is that this transaction should also contain a signature by Alice, because these 5 Bitcoins belong to Alice. So if this transaction is going to spend these 5 Bitcoins and transfer them to Bob, then that should be, of course, authorized by Alice. So this transaction needs a signature by Alice. So in other words, our transactions don't have just inputs and outputs. They also have a bunch of signatures. And I say signatures because there might be more than one signature needed. Okay? For example, we might have a case where, let's say, Alice and someone else, for example, Carol, want to each send 5 Bitcoin to Bob. If this happens, then what we can do is that, again, we create a transaction and we find the previous transaction where Alice received 5 Bitcoins. So I'm going to just write it in a very short way. So I just write 5 Alice to mean that this was an output that gave 5 Bitcoins to Alice. Okay. Then I have to find another transaction, let's say transaction 2, or maybe the same, it might be the same transaction, I don't know. Anyway, I have to find another transaction that gives 5 Bitcoins to Carol. And then I have to take this output and put it also as another input to my main transaction that I'm creating here. And then as the output, I can just say, give 10 Bitcoins to Bob. And of course, now because these 5 Bitcoins belong to Alice and these 5 Bitcoins belong to Carol, then this whole transaction should now be signed by both Alice and Carol. So that's why I said signatures and not just one signature. So this is signed by both Alice and Carol. Okay. So the way we think about this is that no one has an account. It's not like Alice has an account that has a specific balance. What Alice has is a bunch of outputs that she controls, right? So Alice might have received money in a lot of different transactions, and she has all of those outputs. And what she can do is that she can use those outputs in future transactions. Sometimes the outputs are actually also called coins. So, because intuitively, when you think about it, you own an output. So that's like owning a coin, and you can spend that coin. Okay. So this is the unit of, this is the most important kind of object that we have in Bitcoin, a transaction. Okay, now let me just answer your questions and then I'll come back. Okay, someone asked what happens if you need to use multiple transactions as input. Well, first of all, you don't use transactions as input, you use outputs of previous transactions as input. So if you use multiple outputs, you need one signature for each one of them. So every owner of an output that is used in this transaction has to sign this transaction and actually authorize the use of the funds. Okay, someone asked what is the input for the first transaction? That's a great question. I will come back to this later on when we talk about the chain. Okay. So another good question here is, what if there is no single transaction that gives Alice 5 Bitcoin in the first place? Does there need to be multiple inputs that add up to at least the output amount? Okay. So what happens, let's get rid of Carol here. And let's say that again, I have Alice. And Alice wants to send, or actually, let me put that back. Okay, let's just look back at our previous situation. Let's say that Alice and Carol want to each send 5 Bitcoins to Bob, but Alice doesn't have 5 Bitcoins as an output. Or maybe it is the case that Alice has more than 5 Bitcoins. So let's see each case. So here's one case. Suppose that here, Alice received, for example, 12 Bitcoins. And let's say that this is Alice's only output. The only coin that Alice actually controls is worth 12 Bitcoins. But now she wants to pay only 5 Bitcoins to Bob. And again, let's say that 5 Bitcoins is also paid by Carol. So what we can do is that we can use the same output here as an input to this transaction, but then we can also create another output from this transaction. And we can say that this transaction pays 10 units or 10 Bitcoins to Bob, but it also pays 7 to Alice. Okay? So in a sense, Alice can get the change back in this transaction. Okay? So this is how we can use larger amounts. But what if Alice has, for example, a bunch of outputs that are each worth just 1 Bitcoin? Well, she can just add all of them as inputs here. So she can add as many outputs or coins that she owns as inputs to a particular transaction. And if the sum exceeds the amount that she wants to pay, then she can create another output that pays the rest to herself. And then she can sign this transaction. And by the way, the signatures are basically authenticating every input and every output. So what Alice is signing is that I'm giving these particular coins to this transaction, assuming that they are distributed like this. So you cannot change the distribution after the signatures. Okay? So, another question is that if only one of the signatures in a transaction is invalid, does it make the whole transaction invalid? Yes. All the signatures should be valid, otherwise it's just not a valid transaction and it will be treated like trash. No one cares about it. So another question is that, so the transaction made by Bob will have the signature of Carol and Alice. Well, we don't really specify who makes this transaction, who forms this whole transaction, but usually the payers will form the transaction. So usually what Bob does is that Bob just tells Alice and Carol that this is my public key, please send this much money to this public key. And then Alice and Carol are the ones who make this transaction and sign it. and then publish it on the network. Okay. Will there be a transaction fee? Yes, we will talk about transaction fees a little bit later. Another question is, how can Alice check the total Bitcoin she has? So, as I said before, Alice does not have any kind of account with a balance. All she has is a bunch of outputs. And the way that she can check that is that she can go through every transaction that is recorded and see all the outputs that belong to her, that have her public key, or if she has several public keys, all the outputs that belong to at least one of her public keys, and then she can just sum them up. So basically, you have to compute your balance on your own. It's not something that is inherent in the system. And actually, most of the wallet apps that people use for Bitcoin does this automatically. So what you as an end user will see in your wallet application is that you have this particular balance, but that's not what's recorded on the blockchain. Okay. So another question is, what is the data structure of the transactions? I'll come back to that as well. For the details of that, actually, you can just read Bitcoin's white paper or any cryptocurrencies white paper. Again, we mostly care about the ideas here and not about the actual implementation. Okay. So someone else asks, since there is no centralized bank, how do we know if there has been illegal activity? For example, lots of money being sent to one specific key. We can't. So, well, all the activity is public, so we can figure out that there has been some sort of illegal activity or do something like KYC and AML and so on. But actually, there is no central bank, so there is no one who can stop this illegal activity. If the illegal activity is not illegal according to the algorithmic rules of the blockchain. Another question is, so Bob tells Alice to send the Bitcoin to the recipient's public key? Yes. So Bob just gives his public key to Alice, or maybe the hash of his public key to Alice, and says, sends this much Bitcoin to this address or to this identity. Oh, and by the way, I generally, when I talk about identity or public key or address, they're all the same thing. So I use all three of these words and they all mean the same. Okay. Another question is, what if the output public key is invalid? Is the money going to be lost? Yes. So one important point here is that since anyone can create identities for themselves, and since there are no accounts, there's no central accounting system, there is no way to know if when you have an output here that says 10 Bitcoins go to someone whose public key has the following hash, so it would be like a huge hash of a public key. There is no way to invert this hash, so there is no way to actually find the public key. And even if we know the public key that had this hash, there is no way to verify that that's a valid public key, that it actually belongs to someone, right? Because when people create their keys, they don't announce it to anyone. They just do this, they create a private key and a public key, and that's it. So actually, you have no way of saying if someone actually controls the identity that you are sending some money to. And if you make a mistake and you send the money to an identity that is not controlled by anyone, so for example, to a public key that doesn't have a corresponding secret key that someone knows, then that money is lost. It's basically burned. Okay. So another question is, when first broadcasting the transaction, how do we make sure that the data can't be traced back to a physical device or an IP? Well, blockchain doesn't really solve this problem, but what you can do is that you can just use a VPN, or you can use systems like Tor that are used for masking your IP and making sure no one finds out. Okay, so let me go back to transactions and continue here. So we talked about inputs and we talked about outputs, but let's now be a bit more formal about validity of a transaction. So I actually covered most of this already, but let's just be formal about it. So when is a transaction valid? What are the requirements in order for us to be able to accept a particular transaction? Well, I already talked about the signatures, right? So the very first requirement is that it should have valid signatures from anyone who owns any of the inputs, from all owners of inputs. So here, if I have an input from Alice and I have an input from Carol, I should have a valid signature from both Alice and Carol. And of course, this signature should sign the whole transaction. So it's not okay if I just have a signature from Alice that says, yeah, I'm fine spending 12 Bitcoins. It should be a signature from Alice that says, I'm fine spending 12 Bitcoins in this particular transaction that gives 10 Bitcoins to Bob and 7 to myself. Okay, so the signature should cover the whole transaction. So that's the first part. What else do we need? Well, the transactions should not be able to create new money, right? So in other words, if I put 5 Bitcoins in, I shouldn't be able to take 10 Bitcoins out. That's very simple. So the sum of all inputs should be smaller than or equal, sorry, should be larger than or equal to the sum of all outputs. So this is our second property. So the sum of inputs should be larger than or equal to the sum of outputs. So some of you might ask, why shouldn't it be exactly equal? And actually, maybe in some cryptocurrencies, the rule is that it should be exactly equal. In Bitcoin, we don't have that rule. So you can actually burn money. You can create a transaction that gets 5 Bitcoins as input, but gives out only 3 Bitcoins as output. And that's effectively burning that money. But later on, we will see that this particular kind of burning has a nice meaning in Bitcoin, and it's actually useful to have it. Okay? But there is another really important thing. And the other important property that we need here is that every output should be used only once. So suppose that I am Alice and I got this transaction that gave me 12 Bitcoins in this output. I should be able to use this particular output only once. Because if I use it twice, that's effectively me printing new money, right? And that shouldn't be allowed. So what we say here, the term is that usually we call it double spending. So we say double spending is not allowed. And what that means is that every output can be used only once as an input in a future transaction. If someone gives you a transaction, and let's say that you also magically know the history of all transactions that came before this, then you can verify all of these, right? So you can verify that it has all the right signatures, because verifying a signature is very easy. Actually, in Bitcoin, we don't use RSA signatures. We use a different kind of signature, but it doesn't matter. The idea is that whenever you have a digital signature, you are able to verify the signature efficiently. And in order to verify a signature, you just need the public key, and the public keys are in the transactions, so you can verify the signatures. So that's good. This one is also quite easy to verify. So you can just say, I just sum up all the inputs and sum up all the outputs and make sure that no new units of currency are created. The last part is the part that is the hardest. So if we want to make sure that there is no double spending, I can't just check this looking at the current transaction or at the transactions that are referenced in it as at the previous transactions. What I have to do is that I have to go through the whole history of all the transactions that existed in my system, and I have to make sure that none of the previous transactions use any of the outputs that is used in this particular transaction. So as we will see, double spending and avoiding double spending is going to be the hardest problem that we have when we are working with these cryptocurrencies. Okay. And this takes us to the idea of a ledger. So if I want to just put it here, taking double spending, this needs the history of all transactions, because otherwise I can't check if something is double spent or not. Okay. So let's give a very simple way of having this, having a history. Before doing that, let me just tell you what the main problem here is. The main problem is that at the end of the day, we want to have a decentralized currency. So we want everyone to be equal. We don't want anyone to have more privileges or more information than anyone else on our network. But if that's the case, then we have to make sure that everyone has the same history of transactions. So everyone on the network should agree about the transactions that have happened until this point in time, because that's what they need in order to be able to verify that a particular transaction is valid. Right? They have to check that there's no double spending. It's going to take us a little bit of time to get there and get a completely decentralized solution. So first, let's talk about a centralized solution. And what is a centralized solution that we can have? And when I say centralized, again, I mean that we have, for example, a central bank. So what we can do is that we can have a central bank that just keeps track of the history of all transactions and puts these transactions on a website or gives some API such that anyone can access them. Anyway, publicly publishes the list of all previous transactions. And let's say that we just agree that the bank's record is always correct. Okay? So this is what we would call a centralized ledger. So there is a central bank that keeps track of the history of all transactions. And not only it keeps track, but it also publishes the history. Okay, so, and also publishes the history so that everyone can see the history. Okay, so this is already not good because we didn't want to have a central bank, but let's say we have it for now, we will remove it later. What are the properties that we want to have? The property that we want to have is that we want to make sure that this bank is not cheating. We want to make sure that the bank does not change the history. And how can we make sure that the bank does not change the history? Well, several sessions back, we actually talked about this problem. We talked about this idea. It was this one. that you have a bank and the bank is keeping track of the list of transactions in your own personal account, but you don't trust the bank and you think that maybe the bank wants to change the history of transactions. So the way that you can keep track of it and make sure that the bank cannot change the history of transactions was to use a linked list with hash pointers. Okay? So here we can do something very similar. We can say that the bank just keeps track of the history of all transactions and everyone else verifies the bank's work. So instead of these just being transactions on your account, the bank is now keeping track of all the transactions in the currency system, all the transactions that are made by everyone at any time. Okay? But again, the verification is just as before. So if the bank just puts these transactions in a linked list that have hash pointers, then everyone can verify that the bank is not changing the transactions. And well, again, there's nothing that actually stops the bank from changing, but it's that if the bank changes even one transaction, then they have to change the whole history and all the hashes and everything. And then everyone else would be able to say that the bank is cheating. And actually, we can go one step further. And we can say that when we have this sequence of transactions that are connected by hash pointers, we also have the bank's signature on every single transaction. So let's say that the bank's, if this is, let's say, transaction 1, then the bank signs it, S1. If this is transaction 2, then the bank also signs this one. And we can use any kind of data structure that we want. We can actually put the signature inside the transaction itself. But the idea is that SI is the signature of the bank on transaction I. Okay? And now if the bank cheats, if the bank tries to change the history of transactions, then anyone who has kept track can produce a sequence of transactions that are now changed, but are signed by the bank. So it's provable if the bank tries to change something. And for example, if we implement this in the real world, then what would happen is that the customers can take the bank to the court and show that the bank actually changed some transactions and tried to do fraud. Okay? So this is the structure that we can have right now. This is, again, the same structure that we talked about before. We just have a bunch of transactions, and they are chained together with hash pointers. So these are hash pointers. But the only difference from before is that we also include digital signatures of the bank on every single transaction. And this is so as to make sure that only the bank is actually writing these, writing this whole ledger. Let's call it a ledger. So we called it a linked list before, but now I want to call it a ledger because that's the word that we use in the cryptocurrency systems. But there is a slight problem here. So suppose that, for example, Alice sends some money to Bob. So Alice creates a transaction, let's say transaction 1, and signs this transaction, which says, use this output that belongs to me to pay Bob. And then what she has to do is that she has to somehow send this transaction to the bank. So suppose that Alice sends this transaction to the bank. The bank can just ignore it, right? Because there is nothing that forces the bank to include all these transactions into the ledger. The only thing that we can check is if the bank is actually changing the ledger, is changing something that happened before. We cannot check that the bank is maliciously trying to not accept transactions from a particular person. For example, maybe the bank doesn't like Alice and doesn't want to let Alice do transactions. So that's one of the dangers of centralization. You can basically blacklist people. Now, that's the first problem. The second problem here is that in order to make sure that the bank is not cheating, every customer is basically keeping track of this ledger and all the hashes and all the signatures, but there might be too many of these. So again, think of all the financial transactions in the world in a particular day. There are maybe millions or even billions of transactions. So you don't want to have a linked list that is that long, because if you have a linked list that is so long, it's really hard to find anything in this linked list. So instead of doing that, we use the idea of blocks. Okay? And a block is basically a set of transactions and we can put a size limit on the block. We can say that every block is at most, for example, 1 megabyte, or it's at most 1 gigabyte, or whatever. We can have a fixed size for each one of our blocks. So we just use fixed size blocks. Okay? And let's call these blocks B1, B2, and so on. So each one of these is just a set of transactions. And what the bank does is that it creates a linked list of blocks instead of creating a linked list of transactions. So I have block 1, block 2, so on, and I have signatures of the bank on those blocks instead of the transactions. I'm sorry, I'm going a bit overtime today. And now the next question is, well, how do we store a block? Because this whole idea was that so that we can shorten the amount of storage that we have here and the amount of things that people have to check. And I have already solved that as well. So if we have a set of stuff and we want to make sure that we save them in a way that is tamper-free, we saw before that we can do this using a Merkle tree. So I can say that each block BI is a Merkle tree of transactions. So each block BI can have a lot of transactions in it. Maybe it has 1,000 transactions in it. But these transactions are saved as a Merkle tree. And so we can just have the hash of the top of the Merkle tree to denote our block. And that's what we will save in our ledger. So we will just save the hash of this block 1 in the ledger, and then we will have the hash of block 2 and so on. So, and this hash is, again, as we talked about it before, the root of the Merkle tree, right? And then these signatures are also on those hashes. Okay? So basically what the bank is doing is that it's just publishing the list of hashes of all the blocks and signing them and committing to them. And of course, the bank also publishes the blocks themselves and the transactions, but those are not included in the ledger. The ledger only contains the hashes and the signatures. And if someone wants to make sure that the bank is not cheating, that the bank is not changing the history, they can just check that the ledger is not changed, which we saw is super easy. You just need to check one hash. That's what we covered before, like several sessions back when we were doing this thing. So this is the exact same thing as before. Okay, so that's all for today. This is the end of this session. I will just stay and answer questions, but you guys can leave. And I'll see you all in the next session to talk more about how Bitcoin works and how to make this actually decentralized. Okay, so let me look at the questions here. So one question is, in this case, can a bunch of verifiers maliciously frame the bank when the bank didn't do anything wrong? No. So how can you, let's actually think about this. How do you prove that the bank has done something wrong? The way you would do that is that you will give me a ledger that differs from the current ledger. So you will give me a bunch of linked list nodes such that at some point they diverge from what's currently on the bank's website. And you also say the bank gave this to me. And the way that you can prove that the bank actually gave it to you is that you have to show the signature of the bank on every single node, right? So assume that you cannot forge the signature of the bank, which is one of the main assumptions that we have with digital signatures. You cannot frame the bank. You cannot say that the bank did something wrong. But if the bank actually does something wrong, if the bank actually creates a fork like this and says this is valid to some of the people and says this one is valid to others, then they can put these two together and all of them have valid signatures of the bank and also valid hash pointers. So they can prove that the bank actually did something malicious and tried to change this history here. So that's the nice thing about it. You can prove that the bank did something wrong, but if the bank doesn't do anything wrong, then creating that proof needs a forgery of the bank's signature, which we assume is impossible. Okay. So the other question I see here is, what does it mean to sign a block? And as I said, when I talk about signing a block or signing the hash of the block, I'm thinking of the block as a Merkle tree of the transactions, right? So each block has a bunch of transactions in it, and the way that I've saved that block is using a Merkle tree. So instead of signing the whole block, I can just sign the Merkle root, because the Merkle root, as we saw, would change if we change anything in the block, in the tree, right? So when I say the bank signs every block, what I mean by that is that the bank produces a signature on the top hash, the root hash of the Merkle tree that actually saves that block. Okay. Another question is, could you add the shortcoming you just said about the bank without block to the notes? I'm not sure if I understand this question. Sorry, I didn't really understand what you mean here. If you can rephrase your question, that would be great. So let me go to the next questions. So the next question is, are the signatures by Alice and Carol the same as digital signatures introduced in the last lesson? Yes, they are. Well, they have the same properties, let's say, that we showed in the last session. So they have all of these properties. They are not forgeable. Anyone can only sign for themselves, but when someone signs, everyone else can verify their signature and so on. But actually in Bitcoin, we don't use RSA signatures. So the actual implementation is different from what we had here. But the guarantees and the way that they work for us is the same. So the other question is, if yes, then the signatures from Alice and Carol are decrypted using their own secret key and sent to Bob. No, well, the signatures are public and the transactions are also public. So everyone can see all the transactions. Everyone, okay, let me scroll here. Everyone can see this transaction and everyone can see the signatures on it. So everyone can verify that the signatures are valid. And the signatures are not encrypted, so anyone can see them. And also here, a good point about it is that since all the signatures are publicly verifiable, the bank can produce this ledger. And of course, the bank would also publish the the Merkle trees and all the transactions in the Merkle trees. And everyone can also verify that all the transactions are valid. So everyone can verify that the bank is not letting an invalid transaction into the chain. That's also a really nice property that we have here. Okay, going back. Okay, about the previous question. So the shortcoming is about why we're introducing the block, because we might have too many transactions. Can we add it to notes? What does it mean to add it to notes? Oh, to the lecture notes. Yes, sorry. So I was thinking about notes on the blockchain. Yes, I will just, I will write it somewhere here. That's fine. Okay. Yeah. Okay, any other questions? I will add this later here, and then when I put it on Canvas, it would be good. Okay, no more questions. Great. So I'll see you on the next session.